So now we have learned a framework, which is, let's say, empirical risk minimization, and another framework, which is cross validation. And let's look at one model so that we can bring in everything together. So let's start with a model called linear regression. So the thing is, it's not like linear regression is coming for the first time in this course. You kind of already know about it. But let's just apply whatever we have learned. So the idea is kind of simple that we have these blue points and we want to fit a linear line to these points. So here we have x-axis for both the cases. And in the second case, we want to fit a quadratic to the points. Otherwise, that's the kind of a simple problem. And in this module only, we will also see examples of what these x should be, which is kind of like feature engineering. But let's work in abstraction for now. So what is the loss function here? What is my loss function? So one option could be half of sum over small n equal to 1 to capital N. And then we have targets, which is yn, which is the height of these points, minus what our model thinks, which is w transpose xn whole square. So what is this formula? So what we do is we kind of find all these vertical lines. Basically, that is the gap, right? Yn minus W transpose Xn. So these points on the line are W transpose Xn's for different values of Xn, right? And once you have these vertical lines, what you can do is you can kind of square them, add them, and half is just there because if you take the derivative, this 2 cancels out with this half. That's the only reason we have a half. So basically, I call this RSS of parameters W. RSS is basically residual sum of squares. So I hope this loss function is clear to you. Now the next thing is, where is it coming from? And like one way to look at it would be like, if you assume these vertical lines are epsilon, then one way to say would be like these epsilon is distributed according to a normal distribution with mean 0 and standard deviation, let's say sigma or something, right? Or variance sigma square. So that's kind of the idea. So with if I think about it that way, I can say that my negative log likelihood of W is equals to negative sign for negative, and then log likelihood, which will be like log of the formula for normal distribution, right? And in higher dimension, the formula is 1 by, okay, it's higher dimension, so let's write 2 pi sigma square to the power half. And by the way, this is not for higher dimension because in higher dimension, it will be something like to the power d. Anyways, let's proceed into exponential of minus 1 by 2 sigma square into yn minus w transpose xn whole square. So this is basically for my nth data point. And of course, my likelihood is basically product of all these things inside. And if I take that product outside of log, I get a summation n equal to 1 to capital N. And this is my negative log likelihood. And if you kind of expand it a bit, you'll see that you get something like this, which is like, let's say n by 2 log of 2 pi sigma square plus this log and this exponential kind of cancels out. And this minus sign will also cancel out. So you get 1 by 2 sigma square, sum over I equal to 1 to n, then yi minus w transpose xi square. And the thing is, basically sometimes people ask, like, what is the assumption of a linear regression? So first assumption obviously is that the errors are normally distributed. The second assumption, because if I compare this least square or residual sum of squares, this loss function, which is very common in linear regression, how can I relate these two, right? So the first relationship could be like if sigma is constant, like it's not part of my parameters, that I kind of assume that sigma is the same everywhere. If that's the case, I could ignore sigmas, right? Because if you take the gradients, the first term goes away because there are no parameters because it's just a function of w. And the second term is also like you get a gradient, but then you have a multiplier of 1 by sigma square. But eventually you will say that the gradient of negative log likelihood with respect to w is equal to 0. So again, this sigma square also is kind of not involved at all. So the assumptions, right? The first assumption is that your error is Gaussian. The second assumption is that your sigma square is same everywhere. And basically it also has a name. Sigma square is the same everywhere. It has a name. It's called homoscedasticity. But then you'll say that if sigma square is the same everywhere is the assumption, what's the alternate? The alternate is that the sigma could be a function of x and then squared. If that's the assumption, then basically your sigma is changing. I'll show you two examples very soon. And if sigma is a function of x, that is it's changing, in that situation it's called heteroscedasticity. Now the thing is, uh, if you know what it means, it's fine. I mean, anyways, like this is two of them. The third one, which we had already seen before, is the issue of multicollinearity. So this is number one, which is basically all the errors are Gaussian distributed, and all these errors are kind of IID in some sense, IID, because that's how I formed my likelihood and things like that, right? Obviously, the linearity assumption, because it's a linear regression, linearity assumption, because my model itself is linear, right? I'm assuming that yn can be represented as W transpose XN. IID kind of gives in like independence also, and then identically distributed also. So in some sense, this IID tells you a lot. And then second one is basically homoscedasticity, which just says that sigma square is the same everywhere. So actually, in negative log likelihood, I can ignore sigma as well. I mean, it depends. If you want to learn it, you can do that as well. But if I wanted to relate this loss function with residual sum of squares, then that's what I would have to do. And then the third one was no multicollinearity. And the fourth one is basically linear assumption, which is I'm saying that yn can be predicted based on just a function, which is W transpose xn, or even f of xn, right? In this case, it's a linear function. That's why linearity assumption, but it could also be even complex things and things like that. And we had also seen before that W transpose phi of x can actually map an x into a higher dimension. And there you could also do some non-linear stuff. But it is always linear in W. Okay. So anyways, this residual sum of squared error, which is the usual loss function we have for linear regression. Okay, before we continue, I'll just show you. Okay. So this is what I wanted to show you. What is an example of homoscedasticity? You can see here that all the data points, whatever is my x value, the spread is kind of in a narrow band. So that's how I can say that the variance is kind of the same everywhere. Here it's an example of heteroscedasticity where as I increase my x, my variance is also increasing. So if this kind of data we have, we might have to model heteroscedasticity in some way. Either ways, like what I'm trying to say is I just wanted to explain you what is the meaning of these things and what are the assumptions of a linear regression. So let's get back. So once you have your loss function, which is basically just half of sum over n equal to 1 to capital N yn minus w transpose xn whole square. So basically, this is my loss function, and this is a loss function for something called ordinary least squares. Why? Because eventually I will minimize this loss function. So first thing is it is the sum of squared and minimizing. So that's what least squares means here. And of course, we have learned optimization and we can find the gradient of this loss function with respect to W. And actually, this formula is very readable, but there's also short form for this. You can write this quantity as half of norm of y vector, where every entry is a scalar value in the data set. If you have n data points, this vector is of length n, and then you have x times w whole square, and this is an L2 norm. And L2 norm squared can also be written as half of y minus xw transpose times y minus xw. Anyways, I'm just writing equivalent forms of loss function, and if you find a derivative or gradient of these things with respect to w, what you'll get is something like this: x transpose x w minus x transpose y. And of course, either you can do a gradient descent based on this, which is fine, but you could also equate it to zero because that's the optimality condition if it is possible to derive w. And at least in this case, it is possible. So you do that. So basically, you can see that this transpose xw is equals to x transpose y. And then you can take an inverse of x transpose x. Eventually, what you'll get is your estimate of w, which is w hat, which is equals to x transpose x inverse x transpose y, right? So this is a closed form solution for ordinary least squares. And of course, it is possible for you to do gradient descent and find W iteratively. That's also possible. And if you take the double derivative, then the Hessian of W will be just x transpose x. And it's not that difficult to prove that this is positive semi-definite. So basically what it's saying that your loss function looks something like this, which is also not that surprising. Okay. So that's one part. One more part is basically if I look at this, I'll clean this up a bit. So now I have these blue points here, and ideally I want to fit a line which is the best in some sense. And the definition of best is that the loss is lowest at that location. Now let us kind of in the corner plot my loss function. Where do I do it? Okay, let's do it in this corner. So let's say this is my loss function, right? Now what happens is I get started at some location. So here my x-axis is W and y-axis is my loss, L of W. Okay. So usually you start at some random location, let's say W0. And at that random location, you'll have this loss function, which is reasonably high. This, and let's say that is kind of a line which looks something like this. Then you do a gradient descent. The gradient descent tells you to take a small step in this direction. So you'll reach a new location, let's say this location, and your loss has been lowered in this direction. It has gone down. And then you have a new W location, which is, let's say, W1. And let's say that W1 is slightly better than the previous one. So let's say the new W, so this is my W0 hyperplane. Then it's slightly better now. So maybe this is how the line looks like. So let's say this is my W1 line. Again, gradient descent tells me that go to the left. So I take a small step towards the left and I reach my W2. And this is my new loss. And again, my loss has gone down. Again, my line will be slightly better fit to the data points. Let's say it looks something like this. And this is my W2. Again, gradient descent tells me to take a step towards left. So I take that step. I reach my W3. Again, my loss has gone down. And now I'll kind of start getting closer to this blue line. Not perfectly the same, So this new line is my W3, and I keep doing it till I converge, right? And eventually what will happen is I'll get really close to this blue line, and this is my W hat final, or in terms of optimization problem, this is my kind of my W star, right? So, uh, so that's the process of doing gradient descent if you wanted to do gradient descent. So now we know various ways to kind of solve this ordinary least squares problem. Okay. So at least via gradient descent, there's no issue at all. You can find the optimal solution using gradient descent again and again. But if you remember, this W hat was equal to X transpose X inverse X transpose Y. And the thing is, this quantity has a name. So let's say we write it as X plus Y. And this quantity is actually called a pseudo inverse. Anyways, the point is inverting this matrix X transpose X. We have to invert this matrix, right? Because it's X transpose X inverse. And actually, it could be problematic because it can happen that my X transpose X is kind of ill conditioned. And what it means is that its inverse is kind of unstable numerically, or it's not possible to find, right? But basically, the thing is that it is possible to kind of do it via linear algebra path. And here you might have to read up a bit and all, but let's see what the solution is. Now the thing is, I'm saying that if this finding this inverse is tricky, one solution we have already discussed, which is gradient descent path. That is clear. That will give you the answer without any issues. Now here I'm saying that if X transpose X is ill conditioned and all, there could be issues. So there is a way to do it in a proper way. So let's say if the dataset size is much greater than the dimensionality of the problem. So what it really means is my X is tall and skinny. So this is how my X matrix looks like. This dimension is N, this dimension is D. Okay. So if that's the case, what we can do is we can say that X is equals to Q times R. You can read about QR decomposition, but that's a kind of factorization in linear algebra where the property of Q is that Q transpose Q is equal to identity matrix, right? Anyways, the point is that the goal I had was that X times W is equals to Y, right? And this is the closest form of this where uh, it's kind of based on the system of linear equations. Like this is of the form of Ax equal to B, right? And we have to find X. It's the same thing. So if B is in the span of A, then you can solve this linear system of equation and you get your answer. And actually solving this linear system of equation uh, is also kind of equivalent to minimizing X times W minus Y whole square, del 2 norm squared. So anyways, the point is we can substitute this thing. So we get Q times R times W is equals to Y. And then you can multiply Q transpose on both sides. And Q transpose Q is equal to I. So it goes away. So I finally have R into W is equals to Q transpose Y. And then I will take R inverse, which eventually will give me W is equals to R inverse Q transpose Y. Okay. Now, the thing about QR decomposition is that Q is my orthonormal, which has this property. R is my upper triangular matrix. Upper triangular matrix. So actually inverting a upper triangular matrix is computationally very efficient. Okay. Anyways, like I am not recommending you should do that. I'm just giving you an alternate. Uh, I have that framework that I will use gradient descent for everything. But in certain problems, you have this flexibility of getting closed form solutions. And it's about computing that closed form solutions very efficiently. But I personally prefer the framework of gradient descent because it's the same for every problem. Now, uh, what we saw was ordinary least squares, OLS. The next one is called a ridge regression. Again, it's kind of very similar to what we had seen. It has kind of a regularizer kind of a thing. So we take our residual sum of square RSS of W And then we just add a regularizer to it, which is lambda times norm of W squared. So this is kind of my new loss function. And this is basically called ridge regression. Now, again, you can obviously minimize this loss function with respect to W and things like that. And kind of again, you can find a gradient of this quantity L of W with respect to W. And again, if you think about it, this RSS W was basically half of norm of X times W minus Y whole square. Plus then we have lambda of norm of W whole squared. And of course, norm of X squared is just equal to X transpose X. So you can use this property and find a derivative or gradient of this loss function. And what you'll eventually get, okay, let's say I remove this half from everywhere. So this is the loss function. So what you'll get is gradient is twice of X transpose X times W minus X transpose Y plus lambda times W. So this is your gradient. Again, you can do your gradient descent and kind of minimize your loss function. And you kind of can get to this W hat, which is the kind of the lowest loss, which you can achieve on your cross validation data. Okay. Or validation data. So that's the idea. Again, there's also a closed form solution because you can also equate this to zero and do the same stuff we did before. There will be a small change because you have this lambda times, so you have this lambda times I times W. So if you take W common for first and third term, I'll not do it all for you, but just roughly telling you what to do. So you have this X transpose X plus lambda times I times W minus X transpose Y, right? Now it's simple again. You can just say that this quantity is some matrix, let's say some matrix Z. So you just have twice of Z times W minus X transpose Y equal to 0. And of course, you can kind of derive for W, right? You have some W star equal to something. So again, doable, not that complicated. And by the way, this lambda here, in this loss function, is a hyperparameter. Hyperparameter, which you have to tune using cross validation. We learned that, right? So this is your job to tune this lambda based on cross validation or validation set ideas, which we discussed in the last video. Otherwise, it's the same. It is just that when you choose the lambda, you kind of have a holdout data set where you try to find which lambda is the best. But once you know your best lambda, you take all your data, training data, you optimize your loss function, and you find your best parameters. So that's the idea. So this is your ridge regression. And now the next category of regression is called a lasso regression. Lasso regression. So again, the idea is kind of simple that we take again your RSS, residual sum of squares, and instead of having an L2 regularizer, we have an L1 regularizer. Okay, and we want to minimize this with respect to W. Again, this lambda is your hyperparameter, and you will use your cross validation set to find the best lambda. And then once you have known your best lambda, you kind of minimize this loss function based on all the training data you have, and then you find your W hat estimate, right? Of course, you know the gradient of this RSS. We have discussed this multiple times. I just wanted to show you the plot for this thing, which is kind of like this, right? If W was a scalar, then it's just modulus of W. So it looks like this. So if I think about the gradient of norm of W, L1 norm, so this slope is basically 45 degrees, okay? So this is W, this is my mod of W. So if W is greater than 0, then the gradient of this quantity will be equal to 1. If W is less than 0, then the gradient will be equal to -1. And if W is equals to 0, then this point is actually non-differentiable. And then there are infinitely many tangents which are possible. But we can choose any one of them. And for example, slope equal to 0 is actually a good candidate. Just for simplicity, we can say that if W equal to 0, I can say that gradient equal to 0. but the slope of any of these things, which is below these, I'll just draw it again. So you have this V structure and you have all this area below this, right? So any line which totally lies below in this shaded region, I'll just change the color. Any line below this V shape in the shaded area is actually a valid line to take, and the slope of that line is like a valid thing. Obviously, it should pass through 0, 0. But if you could have taken any one of these instead of 0, you could have taken A, which is the slope of any of these green lines. There are infinitely many options, and still you'll get a good answer. But for implementation, like there's a simple choice. 0 is the correct answer because it's one of them. And that's how you can find a gradient for kind of different values of W. That's one. Second thing is the discussion of this choice when W equal to 0, right? This is coming from a concept of subgradient or subdifferential, right? And I think we have discussed this before, but either ways, the point is intuitively I've explained it to you. So now you know how to handle a non-differentiable point via subgradients. So that's a very nice trick, which is actually mathematically correct. And if you take the subgradient at non-differentiable point, eventually you will be optimizing the right thing. So again, same thing, like doing gradient descent is simple, right? No issues at all. So one more thing I wanted to talk about for both of these cases, which is or lasso. In both cases, basically the extra regularizer term can come from a prior P of W. So this is like a probabilistic interpretation of the additional term, second term. So in ridge regression, you assume that your W is distributed according to normal distribution. And in Lasso, you assume that your W is distributed according to Laplace distribution. Laplace. And of course, normal distribution, everyone knows. I'll just write down the Laplace distribution for you. So basically, Laplace of W given mu and B is equals to 1 by 2B exponential of minus of mod of W minus mu by B. Excuse me. So that's your Laplace distribution. But for our case, we use Laplace distribution of W given, I set my mu to 0 and I set my B to 1 by lambda. And that's how this lambda relates to Laplace distribution. And this is kind of your prior. And of course, you'll have the similar thing here. And of course, it will be like, again, mean 0 and then sigma square, whatever. And because it's mean 0, you kind of somewhere get norm of W whole squared. And here also, if you take the log and all, and if you assume lambda is a constant, you kind of, when mu is obviously equal to 0, somewhere you'll get a mod of W or L1 norm of W, right? So that's how it works in terms of probabilistic interpretation. And if I added a bit, my negative log likelihood of W in the case of Lasso regression will be just minus of log of P of the dataset given W minus log of P of W given lambda. And we just saw this thing, right? This was my Laplace distribution with mu equal to 0 and B equal to 1 by lambda. Either ways, when you substitute everything here, obviously the first term is your error being normal. So if you substitute everything, what you'll get is xw minus y whole square, L2 norm squared, plus lambda times L1 norm. So that's what you'll get, which is your negative log likelihood. Not exactly. So I'll say it's PANLL, which is kind of like penalized thing, right? So basically, once you optimize this stuff, what you'll get is WMAP, right? Maximum a posteriori, because we have a prior kind of a term here. So anyways, this is also called L1 regularization, right? Okay, I will write it down in a slightly cleaner way. L1 regularization. Okay. Now, these regularization, which is L1 and L2, actually has a different behavior in terms of the kind of solutions it gives us. Okay. So here I'm trying to show you the difference between L2 regularization and L1 regularization. First thing is this contour which you see is the first term, which is basically residual sum of square term, these contours. And then these diagonals are basically constraints. For example, in L2 regularization, this circle, this shaded blue circle, is just the constraint that L2 norm is less than some quantity. Similarly, in L1 regularization, I have this constraint where basically you have this L1 ball, which is L1 norm is less than some quantity. So the optimization problem equivalently is just we want to minimize our residual sum of squares error subject to constraint that L2 regularization is less than some quantity. If it's this case, L1 norm is less than some quantity if this is the case. Now the solutions are very different. If you look at this yellow dot, that's the solution of the optimization. And you'll see that for various data sets, your contours can change and you get any values in this boundary of this sphere, right? In L2 regularization. But if you look at L1 regularization, you'll see that for huge variation of this contour, it is actually at one of the corners here. See? So just focus on the right one for now. You'll see that this contour is kind of moving and this solution is not changing for a huge range, right? And what are these corners actually, right? These are actually sparse solution. This is an example of 2D where one of the axis is 1 and other axis is 0 for each of these points, which is the intersection of this boundary and these axes. For example, this is 1 comma 0, minus 1 comma 0, 0 comma 1, 0 comma minus 1. So there's some zeros for each of these corners. We have 4 corners. Now, just think about it in high dimensions. That's why we say that L1 regularization is giving us sparse solutions. We'll also do a small derivation to see why it gives a sparse solution, but that's the intuition. Another strong intuition is coming from Lagrangian. Let's look at that as well. So this is the Wikipedia page for Lagrange multiplier, and the problem is kind of familiar. So we want to maximize f of x comma y. Variables are x and y, subject to the constraints that g of xy equal to 0. And of course, if you look at the Lagrangian, it will be f of x comma y plus lambda times g of x comma y. And the stationary point for these solutions are just Lagrangian equal to 0, right? We'll discuss that in a bit, but let's look at the intuition first. So the constraint is this red line, okay? I'll just make a copy so that it will be easier to discuss. So this is what we were looking at. And the thing here is this red line is the constraint. And in the problem, it was g of xy equal to 0. And it doesn't matter because you can always bring in c on this side and say that that's the constraint. So this was the constraint, this red line. And you have this multiple contours for various values of f of xy. And here you have d1 is greater than d2 is greater than d3, right? Because the contours are going in. The thing is, this red line is the constraint, so you have to always stay in this red line. But this red line has many contours intersecting it, so you have various choices, right? For example, let's say you're standing here in this point, which is some x1 comma y1. Now, this is not the best solution. Why? Because you can always walk in this direction and move to a new point here, which is let's say x2, y2. And again, this is not the best because again, you can move around and reach here and here and here. But eventually, if you look at this point, I'll call it x star comma y star, you'll see that it is not possible for you to move around. If you move to the left or right in this line from this point, you'll make the situation worse, which is you'll reach a di, which is actually lower than d1. Okay, so The learning here is that you have to stay in this red line, and wherever you have the solution, that will be the best location you can be. And if you move around, you will actually make the solution worse. So the idea is that if you kind of find the gradient of this red line and the gradient of this contour D1, both should be kind of the same, but in opposite direction. That's the optimality condition. Let's look at that. What I said was the Lagrangian L of x comma y comma lambda is equals to f of xy plus lambda times g of xy, right? Now, if I'm saying that gradient of L is equals to 0, what it will mean is the gradient of f of x comma y is equals to minus of lambda of gradient of g of x comma y. So what I'm just trying to say is that gradient at optimality point, the gradient of the loss function and the gradient of the constraint is kind of the same, but in negative direction, kind of. So that's one intuition, that there is a tangent which connects the constraints and the loss function. And at the optimality condition, the constraint gradient and the loss function gradient is kind of the same, but in opposite direction, shown by these two arrows, right? That's first part. Second part is, if I look at these optimization problems, so let's say my negative log likelihood is equals to 1 by 2 yn. Actually, it doesn't matter, but let's write it in vector form, y minus x times w L2 norm squared. So this is my negative log likelihood. And my optimization problem for the first one is I want to minimize my n, l, l of w with respect to w subject to constraint that my L1 norm is less than some upper bound. Similarly, for this problem, I'll have minimized negative log likelihood of w subject to the constraints that my norm, L2 norm is less than equal to b. Or you can even write norm squared, everything is fine. So that's kind of another interpretation, because if you take the Lagrangian of this and this, the form will be kind of similar to what we have seen before, which is basically your negative log likelihood of w plus lambda times w1, and here you'll have negative log likelihood of w plus lambda times of norm of w squared. Now, just from these intuitions which we just saw, the thing is, whatever be the solution, it should be in the shaded area, right? So obviously it could be at any of the boundaries here or here or here or here, wherever, it's fine. But wherever it is, for example, here, if you again look at the tangent here, you'll see that it's actually a common tangent for this blue sphere and these red contours, both of them, right? Similarly, if I look at any of these corners, you'll see that there are infinitely many tangents possible, right? So again, if I use the same principle, so this corner will again have like a common tangent, because there are infinitely many possibilities if I just focus on the blue part. But if I look at the common tangent, there will be a unique one, which is the tangent to this red contour, which touches this corner, and one of the infinitely many possibilities, which is also the same as the tangent to this red contour, right? So that's one more intuition. I mean, of course, I mean, you could also have some solution with very low probability. And it also depends on many things, like what is the value of this b in the constraint. So that b kind of adjusts the size of this diamond shape, right? If b is larger, then the L1 ball will be larger. Anyway, so that's how we are connecting everything here intuitively. So at least you should know what is the shape of the problem and how are any of the gradients related to the shape of the problem. So that's the main idea. Now I just showed you on the LinkedIn page that, okay, I'll clean this up a bit, that basically L1 regularization promotes sparsity in the solution. Sparsity in the solution. So what it means is that if I have a very long vector of W, so many of these values could be zero if I have large enough uh, lambda or small enough b. And some of them will be obviously non-zero. So that's sparsity for you, that many of these values in this vector will be exactly equal to zero. And L1 regularization promotes sparsity. The larger the lambda, for example, here I have like plus lambda times L1 norm, right? So the thing is, L1 regularization promotes sparsity, and one intuition is that geometrically it is more likely to touch at these corners than to touch at these things. That's one. There's also a mathematical way to look at it. I won't go through all of it, but I'll just give you like a high level framework. Okay. So basically, what I'm trying to do is that basically I showed you this diagram that L1 norm promotes sparsity, but intuition is not always enough to convince some people. So what I'll try to do is derive for you something called soft thresholding, which will show you that actually the solution comes out to be sparse under certain assumptions. So let's look at that. So let's start with our loss function, which is a function of W, which was just my negative log likelihood of W plus lambda times L1 norm. Now let's focus on negative log likelihood term. And first, I just want to write it down what it is. So it is basically half of sum over I equal to 1 to n yi minus W transpose xi whole square. So this is my negative log likelihood. And what I want is I want a derivative of this with respect to WD, the dth dimension of this vector W, for only this negative log likelihood term, right? This one is not that difficult. So if I take derivative of this, the 2 comes down, it cancels with this half. And what I'll get is sum over I equal to 1 to capital N yi minus W transpose xi times xi comma d. Because I have taken derivative with respect to d, WD, which is the dth dimension value. So this is what it is. And my claim here is that I can rewrite this as AD times WD minus CD. And I'll tell you what this AD and CD is so that this becomes equal. But my claim is this equation 1, this equation 2 is exactly the same. Let me write down what is AD. It is just n equal to 1 to capital N x n d whole square. And CD is equals to n equal to 1 to capital N x n d yn minus y, sorry, w minus d, which is basically the whole vector w, but after removing the dth dimension. So this is also a vector transpose x n comma minus d. Basically, I just remove the same dimension which I removed from this w vector. Okay. So this is kind of my C. And if you substitute it back, you'll see that it kind of works. Why will it work? Because there's a WD here. So AD into WD becomes basically WD into XND whole square. And if you just focus on this dot product here, W transpose Xi also has a WD times XID term in it. And if you just focus on that term, you'll have WD times XID whole square. So in some sense, if you focus on WD term, you'll see that you have XND whole square. So that's how AD comes in. And because I have taken out AD from this equation 1, because AD times WD is the term involving WD, I have to rewrite the equation 1 in such a way that I remove AD from my equation 1, which is CD in some sense. So just think about it. And basically, you can write it this way. Now, the thing is, the gradient equal to 0 is basically the optimality condition. So you could always write as AD times WD minus CD equal to 0. So WD estimate, which is WD hat, is equals to CD divided by AD. Now, one more thing is CD can also be written in a very compact way. How? If you see the summation over n, right? So n I traced over data points. And if you think about it, I could write this as a dot product because this is indexed by n. This is a residual, which can also be indexed by n. So if I can create very long two vectors for both of these, I could take the dot product and I could get my CD. So that's the idea. So let's just see how I can rewrite CD. So first thing is I am interested in the CD, but let's focus on one thing at a time. So x and d as a vector indexed over n will be x colon comma d. Colon basically says that I take all the n points for dth dimension. So that's the first term. The second term is also basically n dimensional, and I'm writing it down as r of minus d. This is equal to CD is my claim. But what is my RD here? So R minus D is basically this residual term. And of course, this is also indexed by n. So each entry I could fill it up in a vector. So this yn will give me y vector because that's yn in a vectorized form minus this term, which can be written as x colon comma minus d, which is basically I'm saying that I take the input matrix X and I just remove the dth dimension of that matrix and I multiply that matrix with W of minus D. This becomes my R of minus D, which is basically the residual term. So this is my CD. So in some sense, if I bring everything together, and of course AD can also be written in the vector form because there is something squared sum. So it kind of gives a feel of L2 norm squared. So AD can also be written that way. So I'll do that. So finally, my WD hat is equals to CD by AD. This we have seen, but I could write CD in a compact form, which is X colon comma D transpose R minus D. And AD can also be written in a way that I take X colon comma D whole square, L2 norm of it, right? So that's how I'll get the solution if my loss was just negative log likelihood. But obviously that's not true. My loss is negative log likelihood plus lambda times L1 norm of W. But the good thing is I've already derived the gradient of negative log likelihood with respect to WD, and I have to do the same for the second term, and then I could add them, right? So if I take the gradient derivative of this loss function with respect to the WD, so the NLL term actually gave us AD times WD minus CD. This part we have just seen, plus lambda times the derivative of L1 norm of W with respect to WD, right? So let us just first derive it for the second term, this term, and then bring it back all together. So L1 norm is just the absolute values of these things, right? And so on. So it's basically just summation over I equal to 1 to D, absolute value of Wi. So obviously when we are taking the derivative with respect to WD, everything else goes away and there's only absolute value of WD, which you can, x-axis is WD, and absolute value of WD kind of looks like this. And if WD is positive, the slope is +1. If WD is negative, the slope is -1. And if WD is 0, all these lines, right, can actually be a possible candidate for the gradient. So anyways, the point is that if I do that and if I substitute it here, the final answer which I get looks something like this, which is the gradient of the loss function with respect to WD, that is equals to AD WD minus CD minus lambda if WD is less than 0. It will be equal to AD WD minus CD plus lambda if WD is greater than 0. These things are simple. But if WD is equals to 0, then kind of gradient is in a range. So it will be kind of like minus of CD minus lambda minus CD plus lambda. So this is a range. And obviously, it is because WD equal to 0. So first term goes away and the second term has a range because of that subgradient idea that if you have this structure, all these points at this non-differentiable point are possible. So we have a range of gradients. Now, basically, depending on the value of CD, we'll have various solutions when gradient of L of W equal to 0. So again, I'll just kind of have this thing which I got like kind of intuitively, and I'll again bring in three situations. The first situation is when my estimate WD is less than 0. My estimate is basically when WD is less than 0, what is my answer? This quantity should be equal to 0. So finally, WD will be basically CD plus lambda by AD. So if WD is less than 0, then WD hat is equals to CD plus lambda by AD. If W hat D is greater than 0, then WD hat will be equal to, again, the second row equal to 0. So we get CD minus lambda by AD. So we get CD minus lambda by AD. And if WD hat is equals to 0, then because this is a gradient range, this range I'm saying that equals to 0. So kind of I could, in that sense, lambda is already known. It's a hyperparameter. So in some sense, I could kind of think about that CD is in a range. So that's what I'll do. And I'll just say that CD belongs to the range of minus lambda comma lambda, right? So from these three statements, I equated each statements for each situation equal to 0, and I got something out of it. And eventually what I'm trying to say is uh, I kind of know what my WD will be just based on whatever I know, right? I can always compute CD and I know if it's between minus lambda and lambda, then WD should be 0 and things like that, right? So to summarize, what we have got is W hat D, which is a function of CD, is equals to CD plus lambda by AD if CD is less than minus lambda. Why is that? Because this quantity should be less than 0. AD equal to 0 because AD was just norm squared. AD was just norm squared, so it is a positive quantity. So CD is only which could go positive, negative, or 0. And because of that, if WD is less than 0, then numerator should be less than 0. And that's how I can say that CD is less than minus lambda because numerator should be less than 0, right? Similarly, the numerator should be greater than 0. That's how I can say that CD is greater than lambda. So the second situation is basically CD minus lambda by AD if CD is greater than lambda. And it will be equal to 0 if CD is between minus lambda and lambda. And by the way, there is something called a soft thresholding operator or soft thresholding function, which kind of looks like this. I'll first write down the formula soft threshold. It takes two inputs x comma delta, and that is equals to basically the sine, clean it up a bit, the sine or signum of x, which is basically plus 1, minus 1, or 0 based on the value of x, times mod x minus delta plus. And again, basically x plus means max of 0 comma x. So this is called soft thresholding. And if I just think about the formula and if I think about what I've got, I could write this as W hat D is equals to soft threshold of CD by AD, comma lambda by AD. So it's like CD by AD, lambda by AD. And if you look at this figure, this is what it is. This is kind of CD of CK, and you have minus lambda and lambda here. And basically, that's what is happening. That if your CD is between minus lambda and lambda, we make it zero. Otherwise, we shift it by this quantity, right? This is lambda by AD. So we subtract lambda by AD or add lambda by AD, depending on the situation. Okay. So that's kind of soft thresholding. There's also something called hard thresholding, where if CD is between minus lambda and lambda, we make it zero. And if it's outside this range, then we don't change it at all. Versus if I look at this soft thresholding, you'll see that we are actually making it smaller. So this dotted line was the actual value, which was basically this, right? The negative log likelihood thing, CD by 8. But we are in soft thresholding. This dotted line was the expected thing from CD by AD, but we are making it smaller by reducing the height, right? So it's kind of shrinking even outside this minus lambda to lambda for soft thresholding. For hard thresholding, it is not doing anything outside this range. It is just clipping it to zero if it's between minus lambda and lambda, the CD part. And just a couple of names for Lasso is, I'll take a new page. So Lasso has a full form, by the way. And let's do it like it's basically least absolute selection. It's a kind of a shrinkage operator. Shrinkage operator. Now just some connections. For example, if you just do maximum likelihood estimation, or if you just use the negative log likelihood term, we get W hat D MLE, which is equals to CD by AD, right? So this is basically our ordinary least square solution. Then we also have like WD hat ridge. This is for ridge regression. And it is just WD hat MLE divided by 1 plus lambda. So this is my ridge regression. And then we have a lasso regression. So there we have WD hat lasso, which is basically the sine of WD hat MLE times mod of W hat DMLE minus lambda plus. This was the soft thresholding thing, right? And obviously here WDMLE is my CD by AD. So basically that's how all these regularizations are changing our WDMLE in some sense. Because you can write each one of them as a function of WDMLE, right? So they're kind of connected in some sense. And if you think about the first, this WD ridge and WD lasso, we have seen in a diagram how WD lasso is shrinking the coefficients. But in ridge regression also, we are shrinking the coefficients by 1 plus lambda, because lambda is always positive. So if I divide by 1 plus lambda and lambda is positive, then actually I'm reducing the coefficient size in ridge regression with respect to WDMLE, right? So WD ridge is also shrinking things. Now, the thing is, it is also possible to combine lasso and ridge together. So for example, I could define my new loss function, which is a function of W, lambda 1 and lambda 2, which is just norm of y minus x times W whole square plus lambda 1 W1, which is L1 norm, plus lambda 2 L2 norm squared. So we have here combined L1 and L2 together. And it's basically the combination of ridge and lasso regression, and it is called elastic net. Elastic net. So here is a coordinate descent algorithm for lasso. So first thing is we do is we initialize W with this quantity. Then we kind of repeat till convergence. So for each dimension, we find AD and CD. we do our soft thresholding, and we kind of repeat till our WDs stop changing. So that's an example of learning our parameters using Lasso. There's one more algorithm if you wanted to do gradient descent. So the idea is kind of simple, that in gradient descent, what do? You start from some W0, you update it, you get W1, W2, and you repeat this until convergence. Some Wn, which is, let's say, Wn star, whatever. And the idea is that Wt is equals to Wt minus 1. And if I'm doing a minimization, then I'll do minus gradient of loss with respect to W. Add Wt minus 1. Right? That's the iterative update for gradient descent. So the algorithm here is, I could write Wt plus 1 is equals to soft threshold, and inside that you had two values. The first value is Wt minus some rho t times gradient of negative log likelihood with respect to Wt. That's the first input to soft threshold. The second is again this rho t times lambda. So if you iteratively do this also kind of gets you the correct answer. And this method is called ISTA. This is iterative soft thresholding algorithm. So the name doesn't matter, and like I don't even expect you to remember all these things, but at least you know the options. And here, this is basically kind of like an operator, right? Because soft thresholding is an operator which maps Wt to Wt plus 1 here, right? So anyways, the point is soft thresholding is a shrinkage operator, and we can kind of combine it with gradient descent in a certain way to get this final solution. And right now I cannot go into it, but this category of solution comes under something called proximal methods, and it's okay not to understand that. But how it works is that if you want to optimize smooth function with non-smooth penalties, for example, L1 is a non-smooth penalty, then proximal methods are useful, but we have to kind of derive a proximal operator or something like that, which turns out to be this thing. So how to derive is not important, but this is the algorithm. You iteratively do this thing. You find a gradient at Wt for the unpenalized loss, which is gradient of negative log likelihood. And you kind of iteratively do that till Wt minus 1 converges up to some point, right? Anyways, the point is that the gradient methods are the most trustworthy ones because the learnings or how we do it kind of generalizes to all kinds of problems. So even if we have discussed closed form solution for some of them, gradient descent is kind of like the holy grail where I feel like I could almost attempt any problem with gradient descent. Of course, like gradient descent is one example, but there are other unconstrained optimizers. For example, Adam optimizer and things like that, which is also like falls in the category of gradient based optimizer. But anyways, like that's about L1 regularization and Lasso. Now I just briefly wanted to mention robust regression, and I also wanted to mention quantile regression, or at least give you the intuition of it. So first thing about robust regression is earlier we were assuming that our residuals or our errors were coming from a normal distribution, right? Now, instead of normal, you could choose something which is a heavy tail, right? Examples of heavy tail could be like you could choose a student T distribution, you could choose a Laplace distribution. So at least from the robust regression point of view, you could have like a heavy tailed likelihood. And I'll just kind of bring in a table here, which kind of gives us a very good overall bigger picture of all kinds of regression we can do. Okay. So here are these situations. For example, all of them are point estimates, which means that either we are doing MLE or MAP, but we are not interested in the whole distribution of the parameters. So let's say I wanted to do least squares. So here I assume my likelihood is Gaussian and my prior is uniform. If I wanted to do a robust regression, I could choose my likelihood to be a student t distribution, and my prior could be uniform. Or again, there's another option for robust regression, which is like I could choose my likelihood to be Laplace and prior to be uniform again. And if you wanted to do a ridge regression, you could choose likelihood to be a Gaussian and prior to be a Gaussian. And if you wanted to solve a Lasso problem, you choose your likelihood to be a Gaussian and prior to be Laplace distribution, which gives you that L1 regularization. So these are various combinations of regression problem. And based on that, you could choose your likelihood, you could derive your negative log likelihood and make all kinds of assumptions you want and use gradient descent or whatever, right? So let's finally look at quantile regression. But before I go to the general form of quantile regression, this is also linear regression, by the way. But what I wanted to do was like minimize sum over all the data points I equal to 1 to capital N. And then I have this absolute value of yi minus yi hat, right? And I want to optimize with respect to yi hat. Not even I, let's remove y hat, right? That's the parameter. So let's say that's the setup I want to have. Now here you want to derive the gradient here, right? So let's do that. So the gradient, let's say this is my loss function L of y hat. So I want the derivative of L of y hat with respect to y hat. Again, I have this absolute value function, which is kind of tricky, but we know that if it's if the quantity inside is positive, then it's a +1. If the quantity inside is negative, it's a -1. If the quantity inside is 0, then it's a 0, right? That's the idea. So let's assume that the quantity inside is positive, which is yi is greater than y hat. If that's the case, then we just remove the absolute value and find a derivative. And what we'll get is sum over I equal to 1 to n of -1s. Okay, let's not even have a summation because uh, for every yi, I have this condition. So let's do it for each yi. So I'll just remove this part. So if yi is greater than y hat, then I get a -1. If yi is less than y hat, then I get a +1. And if it's equal, then I get a 0. But I have to sum all this stuff, right? So what it really means, if I wanted to equivalently write it, will be number of times this condition is satisfied. So basically it's just summation of all i's where yi is greater than y hat of -1s plus summation of all I where yi is less than y hat for +1s, right? So that's kind of my gradient. Now the thing is, the optimality condition for any loss is that gradient equal to 0, right? And when will the gradient be equal to 0? It will only be equal to 0 when y hat actually is the median, which means that if I sort all my yi values, some permutation of y1, y2, and so on, right? So if I just sort all my yi's, then if I want the gradient to be very close to 0 or exactly equal to 0, then my y hat should be at the median or very close to median. Then only this quantity will get as close to 0 as possible. So even the absolute value kind of a function gives us a solution where y hat is my median, right? And of course, your y hat could also be equal to W transpose xi, right? So that's not the issue. The point is, if y hat is equal to W transpose xi, then it's a conditional median, the solution. If it's y hat, then y hat is equals to the median. Then only this quantity will get as close to 0 as possible. So that's the first part, where I'm showing you a loss function where the solution is the median. So I would say my y hat is equals to the median of the set of yi's from I equal to 1 to capital N. So that's the solution when my loss is absolute sum over all the data points, absolute value of yi minus y hat. then it's a median. But with this intuition, actually I can tune my solution. For example, if you see here, the gradient of positive and negative should be equal, right? That's how it will get as close to zero. So if it's kind of unweighted, then it kind of becomes equal to zero. So that's the place from where we will see that, okay, let's write it down. The gradient of the loss is equals to sum over all the situations when yi is less than y hat plus sum of all the situations when yi is greater than y hat or greater than equal to y hat. So let's say both these terms have uh, some weights, but in the end, the weight should sum to one or something. Uh, but anyways, the point is that if I multiply by half and half in both the cases, median is the location where y hat will go to, right? Because in the end, we want something which is as close to zero as possible for the optimality condition. But what I'm trying to propose here, that if the gradient was equal to tau minus 1 times yi is less than some q, or let's be consistent, because the reference I'm taking is actually Wikipedia, where it is using q, but let's say y hat. And if yi is less than y hat, then okay, so let me just clean this up again. I don't like the way Wikipedia has written it down. So I'll write it as 1 minus tau. Summation of yi is less than q, sorry, y hat, and I have y hat is greater than yi, right? So I will write y hat minus yi, because in the end it was absolute value in the beginning, right? So I'm trying to generalize plus tau times summation when yi is greater than equal to y hat. And because y hat is now less, I will write it down as yi minus y hat. Now, if you just think about this gradient, when tau is equals to 0.5, you get median, which is what? 50 percentile or 50th quantile or quartile, right? So quantile if tau is zero point 0.5. But let's say if tau is 0.9, then it will give you y hat as something which will be 90 percentile or quantile, right? So that's the idea which is coming from the gradients. Now, if I work backwards, that if both the weights were equal, it was just absolute value. And even this absolute value could have been broken down into two parts, which is when yi is less than y hat, when yi is greater than y hat, right? Even for tau equal to zero point 0.5. So that absolute value thing can be written in this way, and it will be the same. If tau equal to zero point 0.5, it's median. If tau equal to zero point 0.9, it will be 90th quantile. So this is my gradient part. But if I work backwards, my loss will also become very similar in some sense. Oh, sorry. This is actually my loss, because here what I wanted was plus ones, and here I wanted was minus ones, right? So I'll just repeat it again. So my gradient was equals to 1 minus tau summation yi is less than y hat, all the plus ones, plus tau times summation of yi is greater than equal to y hat for all the minus ones. So basically that is my gradient, and that is how I can tune my optimal point based on quantile. So if tau is equals to 0.5, obviously this quantity is equal to 0. So if tau equal to 0.5, then y hat is very close to median or 50% quantile or 50th quantile. Or if tau is equals to 0.9, then I could also say that y hat is something which is like 90 percentile, right? So that's the gradient part. If I work backwards, this gradient can be found by this quantity, right? So I'll just do that. So working backwards, my loss function becomes 1 minus tau summation yi is less than y hat plus tau times summation yi is greater than equal to y hat. So when it is greater than equal to, then for it to become positive, it is yi minus y hat. It is just normal brackets, not absolute value. And if y is less than y hat, then we'll have, again, it needs to be positive. So I'll have y hat minus yi. So basically, this is the loss function which gets me to this gradient. So I work backwards and form a loss function where I can adjust my quantile based on this value of tau. And this loss function is the loss function where it's kind of called quantile regression. And you kind of know now, like how to understand this loss function. And obviously, it's based on a data set, which is a sample. So anyway, this is kind of like a sample quantile regression, and there are more complicated ways to write it and things like that. But this loss function is your quantile regression. I'll kind of take a snapshot from Wikipedia so that you can also go back there and find it. So this is my quantile regression formula. And if you wanted to do like linear regression, you can obviously write Q is equals to W transpose Xi, and everything else remains the same. It is a regression problem. It is a linear regression problem, but it is also a quantile regression problem. So that's how you kind of form your quantile regression loss. It is very useful because it kind of gives you a certain range of things. For example, let's say if you had, I don't know if I can find a point cloud for quantile regression. I'm trying to see. Okay, I got one. So here you can see quantile regression, where you can see 95%, 75%, 50%, 25%, and 5%. So quantile regression can actually be used to also model uncertainty because you kind of know the quantile and you know the width of it and things like that. So, and you can also have like asymmetry in it. For example, on one side you could have like 75%, on the other side you could have like 90%. And I mean, it's up to you what you want to do, but quantile regression can give you like a family of curves or linear lines which can help you estimate certain things, including uncertainty. For example, if you do 25 and 75 percentile on your data points, you'll always get a band between 25 and 75. And sometimes you can reject those samples which is outside the band if you don't want to take action where you are not confident and things like that. Anyways, the point is that's how you do quantile regression. And I feel like that's what I had for linear regression. There's nothing else I have to add in terms of technicalities, but obviously, like when you train it, you will use a validation set like we discussed before. So you could do like a fixed 80-20 split if it's a very large data set. You could also do k-fold cross validation if you're not sure if your data is insanely large. But anyways, like either ways, it's fine. That's one thing. Second thing is measurement, which I think, take up collectively in a video. But for example, mean squared error on your test data is an example of a metric you want to use. Another example could be like a mean absolute error, and there are few more. So I'll make a video about it, but that's the bigger picture. And in the end, when you're training, what you really care about is the loss function, and how do you find the parameters which are kind of the best for that loss function. Sometimes it's not possible for example, in the case of neural networks, the loss function looks something like this. So you'll get to some optima, but you don't know whether it's the best because the best could be this one. Maybe this is the best, but you kind of say that whatever is my local optima, that's what I will take. So anyways, these things will come, but that's all about linear regression. And I feel like we have covered a lot in linear regression. And I will add something if I feel like I've missed something. But for now, I think that's it.